Good day, everyone, and welcome again to our webinar presentation. My name is Adam Harris. I'm a Managing Director here at Seatherm Technologies. Very pleased to welcome you to our featured webinar presentation this Thursday, titled Innovations in Thermal Conductivity Testing of Dielectric Materials. We're running these online seminars weekly now, typically at Thursday at 1 o'clock. Eastern. We have a list of other upcoming webinars that we'll post at the end of the presentation. I will be providing a short little intro in this webinar just on the background of who Seatherm Technologies is, what do we do, but I'll be also introducing the star of our show, who is Sarah Ackerman. Sarah is the head of our application development lab here called Thermal Analysis Labs. That's a division of Seatherm Technologies. Sarah is an expert in thermal conductivity characterization as well as broader thermal analysis, and very pleased to have Sarah quarterback these weekly sessions. She does a great job of curating the material around different themes where heat transfer, thermal conductivity are significant factors in terms of product performance, product design, etc. And so today we're focused on looking at dielectrics and how important thermal conductivity is when it comes to advancement and development and use of dielectrics in different application areas. I am recording this presentation. We will make a point of posting this on our website. If you registered for this event, you will automatically receive a link to that recording. Okay, the session should run for approximately 1 hour. We'll try to keep this moving at a fairly fast pace. I am seeing a few comments of folks having some difficulty with the audio. We do encourage you to use Chrome as a browser if you're not already, and to refresh your windows if you are having difficulty with the audio. Short of that, I will ask Rosa to assist in any further troubleshooting there. Okay, so first off, a little bit of background on who Seatherm Technologies is. I see a lot of familiar names on the roster of participants here. I also see a lot of new names. So some of you may not be as familiar with us as an organization. We are focused very specifically, very narrowly on what we do. What we do, I would advocate that we are the best in the world at, and that is at thermal conductivity measurement, particularly in innovating thermal conductivity characterization with the advancements of transient methods, contact-based transient methods for characterizing. Our reason for being, our raison d'etre in life, is to make thermal conductivity easier to measure, more accessible, to allow you to get better representative data under realistic application conditions, and ultimately improve the characterization capabilities that exist on the market today. We've advanced a number of our own proprietary methods, and we've also improved a number of different ASTM and ISO standards for thermal conductivity characterization. And that's what we do. We're not a broad instrumentation vendor. What we focus on, we do really, really well, and are a global leader when it comes to the characterization of thermal conductivity. Overview of our product portfolio, just to get a little bit of an orientation in terms of some of the technologies that are going to be featured in Sarah's presentation. So the image in the middle of the pyramid-shaped box, that is Trident. That is the new instrument that was launched just last year to great fanfare. It's become our most popular product very quickly. It brings together three of the most prominent capabilities in thermal conductivity characterization, and combining the simplicity and ease of use of the modified transient plane source technique, that the sensor that's the metallic cylindrical shape to the lower right of the main Trident controller, with the robustness of the stainless steel needle probe. This is a transient line source sensor, very robust, sheathed in stainless steel, great for testing very sticky samples for dealing with polymer melts and in situations where the material may cure and damage the sensor. The stainless steel sheathing on this is very robust and a great solution there. And then the ultimate complement with these capabilities is TPS, transient plane source, sometimes described as a hot disk style sensor. This is really oriented towards more advanced users. It is more complex to run. You sandwich the sensor in between two samples, but you can do a lot more with it in terms of dealing with thin films, testing samples. You can deal with thinner sheets or slabs of highly conductive materials like copper. So in bringing these three techniques together, you really have the ultimate toolbox for measuring thermal conductivity, and that's embodied in the Trident platform. That was a short little video I played in the intro to the webinar. To the left of this is a very economical offering. This is really oriented towards folks on a budget. So we're seeing a lot of uptake in academic settings, teaching concepts of heat transfer characterization. This is a thermal conductivity kit. It pairs with a laptop. It has the software on the USB stick that provides the data acquisition and the regression analysis all within the same software package. It pairs with the laptop, which you install it on, and then you also add a Keithley source measure unit. So the Keithley provides the data acquisition. The sensor plugs right into the Keithley and allows you to run measurements. And you can do some very decent experiments with this on solids up to about 65 watts per meter Kelvin. It's a great offering if you're dealing with a very limited budget, but you want to get in the game, so to speak, in terms of measuring thermal conductivity. And that is the thermal conductivity kit. Rosa, I'll ask you just to drop in a link to the thermal conductivity kit page for anyone that's interested in looking more at that. It is available on a Shopify platform, so you can certainly have a look at that if it's of interest. It's a great low-cost option. Lastly, on the right is the TX Touch Experience platform. This is really for characterizing warm feel or cool touch. So the other two instruments are really about measuring thermal conductivity. With TX, it leverages another thermophysical property that we're also measuring called thermal effusivity. Effusivity is sometimes called thermal inertia. It is used to quantify touch performance, so how warm or cool a material feels to the touch. This is a very significant interest in the textile field in consumer goods, where that perception of warmth or coolness or what something feels like when you touch it is very important and often a critical performance attribute for the apparel or clothing or product. Today's topic doesn't really have a lot of lap over with touch properties, so we won't dig into that further today. But if you're interested, we have other webinars that go into great depth on characterizing touch properties, warm feel or cool touch. So today you'll see content more focused on Trident, and again, Trident brings together those three different methods for thermal conductivity. Our tagline on this is "It's better to have options." In thermal conductivity characterization, there is no silver bullet, so to speak, in terms of a method that can test all the different types of sample formats that we will run into in need of thermal conductivity characterization. So testing liquids, testing insulating materials versus testing very conductive materials. So you think of like a foam insulation versus testing a really conductive piece of metal like copper. These quite often are requiring different methods, or at least methods have a better accuracy and precision with these different types of materials. So it's more nuanced when you come to thermal conductivity, and what's really important ultimately is to have some different options available to you so you can pick the best tool for the job. And so what we focused on with the development of Trident, which was a multi-million-dollar investment product development from our side, It took several years to develop and perfect, and was just launched last year. It brings together the three most prominent test methods in transient contact thermal conductivity measurement. And those are the transient plane source, the transient line source, transient plane source. The modified transient plane source is a single-sided test. It's very novel in that way and very simple and easy to use. Again, I've described the other techniques and how they complement that earlier. Our philosophy here from the beginning, the development of this was, it's that view when all you have is a hammer, everything looks like a nail. That's a quote by Abraham Maslow. You might remember Maslow from going back to your university days. If you took organizational behavior, he wrote about the hierarchy of needs. Anyways, he's a great author, and this quote really struck home for us when we relate it to the challenge of dealing with different thermal conductivity types of samples and formats and all the different situations you encounter. When you think about what impacts thermal conductivity, any kind of densification to the material, the temperature, if the material is under pressure conditions, these all have an effect on the thermal conductivity. What's really important is to measure these samples under representative conditions for which the application is applied. So if you're in process safety, you really want to make sure that the sample that you're measuring is representative of those process conditions. If it's a 500 bar pressure that sample is typically under, that's what you want to represent in your testing of the material. And that's something that we've really focused over the years, is to make sure we have a range of different capabilities so that you can really represent those test conditions in testing the material. This just gives you a little bit of idea of what those sensors look like in terms of size. It helps inform the minimum sample requirements for running a test. You see that the largest sensor is the needle probe. It's the active area of the sensor is 150 millimeters in length, and you have to fully cover that area with the sample material. So if you've got a really expensive material, this is you're in a development phase, this is not the best method to run because you need a larger volume of it. The TPS in the middle there, you can see noted on screen, it's available in multiple sensor sizes. So this is great because you can deal with some different size formats. You have some flexibility in the sizing of the sensor. The standard sizes on offer are 6, 13, and 30 millimeter diameter sensors. And then there's some ability to customize that further. That sensor is constructed of a nickel foil that's encapsulated in a dielectric polyamide. And then that sandwiches in between two sample materials. And that's how you run the test typically. The last one I mentioned is the MTPS on the far left. And this is in the sense that it's a single-sided sensor. The active area is 18 millimeters in diameter. That's the area that you have to cover. So it offers among the smallest sample size requirements for running a measurement. And the beauty of it is it's very simple to present only one side of a sample. So you don't have to do a bunch of machining on your samples to get any specific formats to them, really, other than just requiring a relatively smooth surface for the 18 millimeter active area of that sensor. This slide just gives you a quick comparison of some of the specs for those different methods. MTPS and Flex TPS, they offer very similar accuracies and precisions overall. MTPS is the easiest to do. If you had different sites around the world running the same test, we would recommend MTPS first because it's the simplest to run. So quite often the variability in performing a test is introduced by the operator, and the simpler you can make it to run the test, the better your statement of reproducibility is between different labs and facilities. So for that reason, MTPS has some significant advantage. But if you get into the more challenging types of samples like thin films, very anisotropic samples, Flex TPS is a really great addition to the offering and gives you some more advanced capabilities. You will require more training for operating the Flex TPS. And then we've talked about the needle. The needle is a more limited range. It's really more meant for polymer melts, soil testing. semi-solids at a range of -55 up to approximately 200 degrees. I moved on from it, but on the slide, I did just note at the bottom that you see a range of different ASTM and ISO standards represented with these methods. So you can just read them there. But D7984, ISO 2207, ASTM D5334, and D5930. So really meeting a range of standards. These are just some of the accessories that are available. So I mentioned testing under representative conditions. I'll just quickly note the picture in the upper right. That's one of our very unique offerings of high pressure cells. As far as I know, I think we're the only group commercially offering high pressure cells for thermal conductivity. This can be very interesting from a process safety perspective, from a wide range of different applications. Accessories you see top left, that's a fluid cell that just sits on top of the MTPS sensor. This can also be used for testing liquids, as you see in the lower left. And then there's a compression test accessory on the lower right. This would be for dealing with any kind of managed compression of a sample. Remember that densification of a sample can significantly impact the effective thermal conductivity. These are additional accessories for TPS, so a sample test rig in the top left, some of the different size TPS sensors available top right. Lower left is one of the higher temperature sensors. We offer sensors up to 500 degrees C for TPS, and then there's a powder test cell in the lower right. Okay, I realize I've probably taken up more than my time, and I want to transition here to Sarah Ackerman's presentation. So as I mentioned earlier, Sarah is an expert in thermal conductivity. She's the head of our application development lab. She loves working with different clients and helping them. The more challenging the situation, I know the more energized Sarah gets to try to assist, and loves those more challenging types of application scenarios where we can support. But one of the things she's been doing to help us, particularly since the COVID hit, is to help curate these different web seminars where we pick a different theme each week. And today's theme is on looking at dielectrics and the different application areas for them and why thermal conductivity is important there. Just before I transition this over to Sarah, Sarah helped author a method selection guide that is, you see a picture there on screen. Rose is going to send a link here in the chat box of where you can access this guide. It's a free technical resource. One of the questions we get is, we talked about, no silver bullet, no magic method there for all scenarios. So how do you know which methods work best for different situations? And Sarah and some of her colleagues have put together this guide, which really helps give a comprehensive review on different thermal conductivity methods. Beyond the ones that we offer, covering steady state methods, high temperature laser flash measurements, but also giving you a good orientation on the transient methods such as MTPS, TPS, transient line source, on where these different test methods make the most sense to apply, where you're going to get the best accuracy in selecting methods. So this is a free resource. Please feel free to download it. It's gotten some great feedback. We know it's a very valuable resource for folks trying to better understand the landscape in terms of thermal conductivity characterization. Okay, with that said, I'm going to stop sharing my slides and pass this over to Sarah. Just bear with us as we make that transition.
Thanks for the introduction, Adam. Please let me know if you can hear me.
Yes, yeah, no problem, Sarah. Coming in loud and clear. Take it away.
Perfect. Okay, so this should be a good talk with exploring different innovations in thermal conductivity testing of various dielectric materials. So I will start off by talking a little bit about what dielectric materials actually are. So generally speaking, dielectric is one of those words that is used a lot in, common use, and the definition used in common use is a bit different from the definition used in the technical sense. It's kind of like theory in as applied to science versus theory in common use that way. So when we're talking about a technical term of a dielectric material, we're referring to an electrical insulator, which is how that word is commonly used in common English. But it's specifically an electrical insulator that can be polarized by the external application of an electric field. Um, and so what you'll see basically is in the case of a polymer that is a dielectric, for example, you'll get polarization of the van der Waals field to oppose the applied electric field to some degree, and that actually helps improve its capability to electrically insulate whatever it's put around. And in the special case where you're looking at something that's maybe a fluid or a liquid crystal or something of that nature, where the molecules can move around and are weakly bonded to each other, you can have the molecules align physically with the electric field along their axis of symmetry, in addition to polarizing in this way. So in terms of where are these sorts of materials applied, you see them a lot in electrical insulation applications. For example, like with undersea communications and electronics cables, like you see on the left-hand side of this slide. Liquid dielectric materials see wide application in transformers and other electrical installations. And then paste style and soft dielectric materials can see application in as thermal interface materials, while solid, more rigid dielectric materials often see application as physical supports for PCBs, for example. The example which comes to mind is the commonly used FR4 board. So when we're talking about dielectric materials, this talk specifically is looking at measuring the thermal conductivity of dielectric materials and looking at why that's important. But we should probably first take a step back and speak about what thermal conductivity itself actually is. So thermal conductivity is defined as the rate of heat flow through a unit area of a material of a certain thickness when a known temperature difference is applied. So you get, when you take that ratio, you get this property that's called the thermal conductivity. And thermal conductivity is an intrinsic property of any pure material. So you'll see thermal conductivities reported for a variety of pure materials like graphite, sapphire, Pyrex, etc. But you'll also sometimes see thermal conductivities reported for composite materials like an FR4 board, as an example. And in that case, it's really more of an apparent thermal conductivity, but commonly the term thermal conductivity is used to apply to both. The important thing to realize about thermal conductivity in the context of dielectrics, and particularly solid dielectric materials, which are very often anisotropic in their structure, is thermal conductivity itself is a tensor property. It is direction dependent in terms of its magnitude. So you do need to define which axis of symmetry you're measuring along if you're measuring an anisotropic sample for its thermal conductivity. Of course, for isotropic samples like many polymers and glasses, direction doesn't really matter because the thermal conductivity is the same in all directions. So we've defined thermal conductivity, but we often get asked why thermal conductivity is important. Like, why do we talk about it? And the reason why thermal conductivity is important is it's really key to designing thermal management strategies and to what dictates the performance of those thermal management strategies. So specifically, as we try to pack more and more into smaller and smaller containers with consumer electronics and various industrial electronics as well, also in the aerospace and aviation industries, we see more and more heat producing electronic elements uh, within the device being packed closer and closer together. So that makes thermal management increasingly challenging in the field of electronics. So when we're looking at thermal conductivity and thermal management of these electronic systems, what we're seeing is that increasingly the thermal properties of parts of the boards and parts of the devices that used to be considered largely irrelevant to the thermal management of the system are becoming more and more important because increasingly we're requiring that a single component like the backboard of a circuit board has to do maybe two or in some cases even jobs. The first one being the job it's actually there to do, but it also is expected to double duty in a thermal management sense as well. Um, and the problem is that, generally speaking, electrical conductivity is correlated pretty strongly with thermal conductivity. So if you want a dielectric board, it needs to have a low electrical conductivity. And for conventional materials, that has a consequence of meaning it's also going to more likely than not have a very low thermal conductivity. So the real challenge is to engineer materials that are going to have a high thermal conductivity but retain the low electrical conductivity to enable optimum performance in dielectric applications. So I'm going to talk about some work we did in collaboration with a Dr. Douglas Brooks from UltraCAD Design. This work was published in Printed Circuit Design and Fab not too long back. And these slides, the content of these slides provided by him at the time of the collaboration. So some history around this. The original design charts that were used for laminate structures like in printed circuit boards were initially intended to be tentative. They were based on some very preliminary data. And the intent always was that be done to kind of confirm that the design charts used in these sort of situations were in fact highly accurate. But unfortunately, because that additional research never happened, what wound up happening was that the tentative just wound up getting taken off of the design chart that was published. This is in the report number 4283 from National Bureau of Standards. And originally there were two charts, one for external traces, which was based on incomplete research, and the second one was for internal traces. And the idea was that internal traces, because there's less air movement, the heat's going to build up faster, so they derated it 50% from the external traces. But all of this was very preliminary, and the idea was that, you know, further research will be done when funding was provided, and the funding just never materialized. So what the preliminary data wound up being the standard for a long time. So up until 2009, this data was what was used in the design and fabrication of PCBs. And in 2009, an updated board or an updated standard for these devices was issued, which you can see in this slide. The challenge was that the design guidance wasn't really representative of real environments, nor was it really representative of real design scenarios. So while it does provide guidance and it is better than what had come before, it's still not as ideal, and additional work needed to be done. And so that's what Doug Brooks and some of his colleagues have really been championing. And you can check out his website for a full list of the 5+ publications he's authored on the subject in recent years, as you can see here. So specifically what he's been looking at is trying to figure out what the specific temperature is on a trace. Because the temperature is key both to the performance of the device, but also to any hazards that might exist. If your device overheats high enough, you might end up with the device shorting out if the dielectric properties break down, or you might end up with in a very worst case scenario, you might wind up with a thermal runaway and a fire hazard. So the key there is to look at what is the temperature on these electronic components and on these electrical traces, so that you can design thermal management to keep the temperature at a safe range. So when you're doing these studies, you need to build a finite element model. So the trace is going to heat just by resistive heating. And it's going to cool by conduction, convection, and by radiation, depending on the temperature at play. And it's going to reach a stable temperature when the cooling, the magnitude of the cooling effect is equal to the magnitude of the heating effects. So in that case, in order to determine what the magnitude of the cooling, the heating side is relatively straightforward. But to determine the magnitude of the cooling, you need to know the heat transfer coefficient into the air, and that is determined by whether or not the air is passively convecting or forced convection, and some shape factors of the geometry. But you also need to know the thermal conductivity into the board that's supporting the trace. So this can, and because these boards are by design, they're anisotropic in their structure, you need to know the in-plane thermal conductivity and also the through-plane. So the challenge is that the thermal conductivity on these boards is often not specified by suppliers, or if it is specified, it's not specified according to the direction. It's just a single number is given, and you have to assume it's isotropic, even though you know it's not. Estimates available in the literature range from a worst case scenario of about 0.3 watt per meter Kelvin up to about 0.8 watt per meter Kelvin. So that's a pretty wide range. It's greater than a factor of 2. And it introduces a lot of uncertainty into numerical modeling. So by in the initial work that he had done, and I'm getting into why he came to us, what he had done was model according to a 0.3 watt per meter Kelvin thermal conductivity of the board material. And what he got by his simulations here is actually that the via temperature, so the via here might be a little bit hard to see without a pointer, but if you look directly above the 60 millimeter mark on the lowest image there, you'll see on the red trace a little dot. That's a via in this finite element analysis model. The via is, its temperature is dictated by the temperature of the trace. It's not dictated by the amount of current flowing through it, which was really something that surprised him and his colleagues. So what he had done was send some build a test board and run an experiment using a 27 micron thick trace and a 200 micron thick trace, as you see here. And so while he was able to verify that the temperature did appear to be related to the temperature of the trace, he had an issue where the simulation didn't match the actual measurement. It was quite a bit off. So he sent us the sample material for actual testing, and we were able to determine the thermal conductivity of the material both in the in-plane and in the through-plane directions. In-plane was about 0.68 watt per meter Kelvin. Through-plane was about 0.51 watt per meter Kelvin. And we did this with the MTPS test method. And the end result of that is actually something that was published in Printed Circuit Design and Fab that you can see in this URL here. So that provided the confirmation for his initial simulations that he felt would verify the fact that the via temperature is dictated by the trace temperature and the trace current, not necessarily by how much current is actually passing through the via itself. So the consequence of that is that you might need quite a bit fewer vias than would be dictated according to these initial guidance documents that don't take into account the cooling provided by the board itself. So with that, we'll move into the next set of application data that I'm going to take a look at, which is looking at thermal conductivity of different radome materials. So radomes are weatherproof structures which are designed to protect radar equipment from the ambient environment. So these can be used on planes and aerospace vehicles, but also in ground installations like you see on the right-hand side here, which is a photo taken in Japan. A good radome material is going to be a dielectric material which is transparent to electromagnetic radiation, lightweight. It's a rare case where you need a lower thermal conductivity and in a dielectric material, and it should have a high mechanical strength to it. So this paper that we're looking at was looking at different types of ceramics which have their porosity tuned for application in aerospace radomes. Some of the advantages of these ceramics is that they have good mechanical properties and high thermal shock resistance, as well as a low dielectric loss and a relatively low sintering temperature. But as a disadvantage, they do have a relatively high dielectric constant, which means they're going to be relatively poorly performing in the application that's needed. So the desire of this project was to tune that dielectric constant to make these materials better suited to the desired application. And the results on this are seen on the right-hand side for the thermal conductivity and on the left-hand side for the thermal conductivity and the right-hand side for the dielectric constant. And you can see that for thermal conductivity, as porosity increases, the PEG content is the pore-forming agent that was used. So as that goes up, so too does porosity. So as the PEG content increases, thermal conductivity decreases, which is as you would expect. Of course, as porosity increases, thermal conductivity usually will decrease in a porous material. And then on the right-hand side, you can see the same trend is observed with regards to dielectric constant, which should also aid in the performance of these materials. The next application paper we'll take a look at is entitled Dielectric Properties and Thermal Conductivity of Graphene Nanoplatelet Filled Polyvinylidene Fluoride and Polymethyl Methacrylate or PMMA blend. So the idea here is to develop new polymer composites for use as thermally conductive but electrically insulative dielectric materials, which will provide lightweight structural support for electronic devices, and also provide good performance as a dielectric material. So on the right-hand side here, you can see an image which I've taken from the paper, which has about 4 weight% of graphene nanoplatelet loading. And so this is basically showing the alignment of those nanoplatelets in the structure. And 7 materials were characterized in the paper. They looked first at the neat PVDF polymer, then at a PVDF and PMMA blend, and then at 5 different composites, each with a different weight% of graphene nanoplatelets loaded into the matrix. So the results are seen on the right-hand side of this slide, and you can see that as the mass fraction of the graphene nanoplatelets increases, so does the apparent thermal conductivity. And the dielectric constant unfortunately showed the opposite loading. However, the authors do point out that in this case, that indicates that these materials might be tunable for use in capacitors, and therefore this work can still have good application in dielectric materials applications. The final application paper from peer-reviewed research that we'll take a look at is entitled Measuring the Thermal Conductivity of Heat Transfer Fluids via the Modified Transient Plane Source MTPS method. So this is published in the Journal of Thermal Analysis and Calorimetry. So the idea here is to look at the thermal conductivity of different transformer fluids, which are used in transformer structures to electrically provide electrical insulation to windings and electrical coils, thus preventing electrical shorts and current leakage, and also to protect the transformer from overheating, as the transformer fluid can act quite efficiently as a heat transfer fluid through passive convection and also through conduction to prevent premature degradation of the transformer. So when you're looking at transformer fluids, the goal is to design a material or a fluid that is going to exhibit thermal stability during across the desired temperature range of operation in the transformer in question. It should also have a high temperature dielectric breakdown point, so we don't want it to easily overheat and have its dielectric behavior break down. We don't want shorts if it gets a little bit warm. We want to keep it performing well as a dielectric at the desired operating temperature and quite a ways above. It should also have a low viscosity, so it flows well and convects well, thus improving its performance as a heat transfer fluid, and a high heat capacity, again, to ensure good performance as a heat transfer fluid. And then it should have a high thermal conductivity, so that in parts of the transformer that are too physically constricted for passive convection to be very efficient, you can still have good heat transfer away from sources of heat. So oftentimes we get asked why thermal conductivity is important. In the case of transformer fluids, it's a very key question. And in this case, the reason is that thermal conductivity of dielectric liquids used in these transformers is really key to predicting the heat transfer, particularly in the physically restrictive geometries that can sometimes occur in them. And so if you need to predict, if you need this information to predict the heat transfer behavior, then it is genuinely a necessity to improve the life expectancy of transformers and similar devices. It will, and this is becoming increasingly important as our society gets ever more appetite for electronic devices, which results in increasing consumption of electric power and increasing demand for electric power, even as the electrical distribution equipment is aging, and therefore its capacity to carry is actually decreasing as far as material. So in this case, we look at two different or three different samples of transformer fluids. Sample A and B are commercially available naphthenic transformer fluids. Sample C is a paraffinic transformer fluid. Generally speaking, paraffinic transformer fluids are more commercially attractive because they're not as prone to contamination with sulfur-containing compounds, and therefore they don't tend to have as corrosive an effect on the transformer electronics. When we're looking at measuring thermal conductivity of liquids, it's important to make sure that what you're measuring is actually the thermal conductivity. By which I mean, of course, in a real-world scenario, you can have more than one heat transfer mechanism occurring simultaneously. So if you have convection and conduction occurring simultaneously, but your test method is assuming only conduction, you're going to get an overestimation of the thermal conductivity of the heat transfer fluid in question. And this is a major source of error in the literature, particularly when looking at reports of novel heat transfer fluids generally. So the key is to make sure that your thermal conductivity test method inhibits the onset of the convection heat transfer mechanism. So we want to keep that fluid still because, of course, convection is transfer of heat through physical motion of a fluid. So we want to keep that fluid still and stagnant during the measurement so that you can look only at the thermal conduction, which is the property of interest to the current measurement. So how do you do that? There's a couple of different ways, but generally speaking, you want to reduce the volume of the fluid that you're using during a measurement. And this is because by reducing the volume, you increase the surface area to volume ratio. And therefore, you increase the frictional effects on the edge of the container that is containing your fluid. And when frictional effects increase, convection decreases. So you're kind of taking advantage of the viscosity of the fluid to inhibit the onset of the natural convection. The second way that you can prevent convection in a thermal conductivity measurement is by limiting, or in an ideal world, you'd be able to eliminate the factors which cause the onset of convection. But of course, we live in the real world and we have to design experiments in the real world. So that's not really possible, but you can severely limit the factors which cause convection. And is a buoyancy effect. So if when a fluid heats up, it becomes less dense, and therefore it's going to want to rise within the fluid container. So by employing a very short duration heat pulse with a low heat flux, you can really severely limit the temperature rise at the interface between the sensor and the sample material, which in turn is going to really prevent the forces that that drive convection from becoming strong enough to overwhelm the frictional forces within the fluid. So the way that you do that is as seen here, using our liquid cell, which enables testing with as little as 1.8 milliliters of fluid, thus maximizing frictional effects and inhibiting the convection, and also using the modified transient plane source test method, which will keep the temperature increase to less than 1 degree Celsius, thus limiting the buoyancy effect which drives the convection engine. And this shows some application data on transformer oil. Blue data here is the measured data, and the black diamonds is a reference data set on the same grade of transformer oil. And then the application highlights you can see here. This is looking at, again, those transformer oil A and B are the two commercial grades of naphthenic transformer oil, and C is the paraffinic transformer oil. And you can see that in addition to being less corrosive than the naphthenic transformer oils, the paraffinic transformer oil is also higher thermal conductivity, so it's also going to be more effective at providing that heat dissipation functionality that we look for in a transformer oil. The next application data I'll take a look at is looking at dielectric papers. When you're looking at dielectric papers, they're often used to provide both electrical insulation and thermal management in electronics assemblies. They're also sometimes used to enable the safe international shipping of batteries and other energy storage devices to prevent electrical shorting. On these materials, there are two key performance attributes. One is that they need to have good dielectric performance, and the second is that they need to have a high thermal conductivity so that they can provide some thermal management effect in addition to the dielectric effect. And this data was collected using the MTPS method, and you can see the test results shown here, looking at two different data sets, one with a 30 mil sample and one with a 60 mil sample, relative to the specification for the dielectric paper material. The next data set is also looking at testing of anisotropic samples. This is looking at an FR4 board that was characterized both in the in-plane and the through-plane direction. So when you're testing anisotropic samples, you can test across, for MTPS, you can test across all of the relevant principal axes by just reorienting the sample over the sensor. And this is because the sensor measures the thermal conductivity in a one-dimensional manner. So that can make it a very quick and easy way of measuring the differences in thermal performance in a direction-dependent way. The next set of application data we'll take a look at is looking at our flex transient plane source method. Specifically looking at the thin film test utility for the transient plane source method. So when you're looking at measuring thin film materials, what you basically do, you can do this with only 2 data points, which is the blank and the sample. But for added certainty, sometimes you want to add an extra couple of layers. But what you do is you basically take a 0 point with no thin film just as your blank, and then you add another layer, and that extra layer of a known thickness will give you the first data point, and then the slope of the line is proportional to your thermal conductivity. So we've collected a variety of data on various thin films that are commercially available that you can see on this slide. In all cases, our agreement with the literature values for these materials is better than 5%. And with that, we'll wrap things up here. I'll hand things back to Adam so he can talk about our upcoming webinars ahead of the Q&A session.
Excellent. Thank you very much, Sarah. Wonderful presentation. A lot of information put together and curated on dielectrics, and you really see the strength of the interplay between some of those different methods, most particularly the MTPS, Modified Transient Plane Source, and the TPS method. So yes, we are coming to an end. I see we're just coming up on the hour, so we're well timed here to bring this towards a close. We are going to keep the lines open a little bit once we stop the recording for a Q&A session. I do see a number of great questions that have come through. We'll attempt to address a number of those questions in the Q&A. Just a couple of quick remarks. We do have a number of upcoming webinars that may be of interest to some of you here. You can register at the link on the screen. I'll also ask Rosa to drop in that link in the chat box just so you can click it directly. Next week, we're going to be looking at cold chain technology. So you see a lot of interest in cold chain technologies as it relates to food transport, food processing. You're seeing greater popularity in those kind of meal delivery services. This puts a lot of pressure on the packaging we use, of course, very important from pharmaceutical, vaccines, any kind of material that's temperature sensitive in which we ship. We need to make sure that that packaging and insulative quality is well characterized as a critical performance attribute. So we'll be looking at a little bit some of those types of user cases next week on the 27th. After that, we have a guest speaker coming from France to talk a little bit about dynamic mechanical analysis. So CTherm is representatives of Metrovid in North America. Metrovid is part of the ACOM corporate group, world leader in DMA for high frequency, high force characterization of dynamic mechanical analysis. They have a really cool robotic system too, the Expander, which automates throughput characterization and DMA work. So this one will be a nice session looking more at the composite testing and some of the different application work supported there. Later in September, towards the middle of the month, we're going to be looking at geological applications, geothermal, and some of the related applications where thermal conductivity plays such an important role. So that said, that's our upcoming list of webinars. I want to thank you very much for taking the time to join us. If anything you've seen here really piqued your interest, if you're interested in learning more, I did see some questions come in on getting links to the application papers that were referenced. So those are typically provided in the follow-up email that we send after the webinar that includes the recording, and we'll make a point to include those links. There are, I see some also questions on quotes or pricing for Trident. If this is something you're interested in getting in, just kind of a budgetary number, we do have a form that we'll offer in the chat box here as well for a quick quote. If you want to just fill in a couple of quick lines, we'll make a point of getting quick pricing information to you. Particularly this time of year, a lot of folks are looking at their CapEx budgets, what's left for this year, and planning for the year ahead. We're certainly happy to support those conversations. There's no pressure, if don't feel that there's any added pressure there. It's just if you're interested. Okay, rather, Sarah, I'll get you to advance the slides. I think we'll move to the Q&A session. But a big thank you to Rosa for helping us moderate the session, to Sarah, who's done a fantastic job curating this material. Really well done, Sarah. And most importantly, to our participants for taking the time to join us today. So thank you very much, everyone. We really appreciate your time. We wish you good health in these challenging times, and also hope to continue this discussion further on. So hopefully this is just the start. Okay, with that said, I think we'll close the recording. Thank you, everyone, and stay online for the Q&A if you'd like to participate in that.